Hello guys, welcome back to the introduction to number theory. Let's discuss the linear representation of the greatest common divisor. What does this mean, a linear representation? This means that for every two elements of a Euclidean ring, there exist x and y. These are coefficients, these will be coefficients, which also belong to the ring, such that the greatest common divisor of a and b is equal to ax plus by, which is what we call the linear representation. On the left-hand side, we have the greatest common divisor of a and b. On the right-hand side, we have linear representation. So, why is this so? This is a statement, and we are going to prove this. Why is it true? Well, actually, it is very easy to be proved from the Euclidean algorithm. Just take a look. We can notice that every remainder in the Euclidean algorithm can be represented linearly through a and b. So, since every remainder can be represented this way, and we know that the greatest common divisor is one of the remainders, so therefore the greatest common divisor can also be represented linearly using a and b. This is the end of the proof, but I believe that Euclidean algorithm is rather large just to prove this linear representation. So let's consider another proof of linear representation of the greatest common divisor, which we call a proof using the extreme method. And this proof, well, it's not that obvious as the proof that uses the Euclidean algorithm, but nevertheless, I think you'll find it interesting. So let's consider all non-zero elements of the ring that can be represented linearly. Well, we understand that there are such elements, so it is a non-empty set. And let's consider the least norm of all the elements of this set. Well, since norm is a non-negative integer, then we understand that there is the least value of the norm. Okay, so we consider such set, and we consider the least norm in this set. Well, if we have the least norm in this set, then there exists an element of the set with such norm. We denote this element by d. So let's d be the element of the set. So we know that d can be represented linearly using a and b, and we denote this representation as shown on the slide. So we say that d is equal to a x0 plus b y0, where d is the very element of M, the set M, with norm equal to m small m. So the least norm in the big set. Let's note that if a and b have some common divisor z, then d must also be divisible by z. Well, actually that's, I think, obvious, because since d is equal to a multiplied by something plus b multiplied by something else, then since a and b are divided by z, then d must also be divisible by z. Therefore, as we know the properties of the norm of d is greater or equal than the norm of any common divisor of a and b. So, this part of the statement we proved. Now, we need to prove that d itself is one of the common divisors of a and b. Why is this so? Well, let's try and divide a into d with remainder. So we say that a is equal to dq plus r, a familiar formula, right? Where r is less than d. But in that case, if r is not 0, then we can represent r as a multiplied by something, plus b multiplied by something else, and this something and something else belong to the ring. So we get that R is also linearly represented in A and B, but R is less than D, which is a contradiction because we took D to be the least element of R, of our Euclidean ring, such that it can be represented linearly using A and B. From this it follows that A is divisible by D, and similarly B is also divisible by D. So we can state that D is actually a common divisor. Earlier we proved that D is greater or equal than any common divisor of A and B, and now, just now, we proved that D is actually one of the common divisors of A and B, which means that D is the greatest common divisor of A and B. So what? Well, let's just remember that D is represented linearly in A and B, as you can see here on the slide. So therefore, we just proved this way that the greatest common divisor of A and B, can be represented linearly using A and B.